Hi, this is Natalie Tipton, and I'm going to talk a little bit about transfer learning today for our end of the year project. So, as we all know, extremely deep neural networks are costly to train as they can take an extremely long time to complete. They can also be difficult to adapt to specific use cases once they've been trained. For example, if you have a network trained to recognize images of cars, it likely won't work well on trucks. A person at home also likely does not have access to resources that are capable of training a very large neural net from scratch to, for example, be able to now recognize truck images as opposed to cars. This is where transfer learning comes in. Transfer learning speeds up the training of extremely deep neural networks by taking existing, pre-trained architectures and training only the output layers on new data. This is different from traditional machine learning because it learns new tasks based on knowledge it already has, as opposed to learning without consideration for those past learnings. For example, ResNet 50 has tens of millions of parameters and took more than a month to train the first time around. Transfer learning allows you to add new output layers to train on, new, slightly different data, without having to train the convolutional layers, which make up most of the network. Transfer learning would be incredibly useful for businesses and independent researchers because it allows quick and efficient use of extremely complex architectures where data may not be abundant. Going back to the ResNet 50 example, we know it is extremely good at image classification, so transfer learning allows it to be further trained on a specific subset of its original dataset, so any sort of real-life objects, to gain extremely good performance with minimal data since the network already has a good idea of how to classify it before further training. To exemplify this, on the image here, only the blue layers with the red box around them would need to be retrained in a transfer learning application. Like anything, transfer learning does have some pitfalls. Since the architectures are so powerful and they are being trained multiple times on similar data, it can be very easy to overfit the model on the training data and have it fail on testing data. For this reason, data cleaning and augmentation is very important. Another pitfall is that an existing model that was trained on very similar data to the data you are looking to train using transfer learning is imperative. For example, the ImageNet was trained on real-life objects, so further training it on X-ray images would not work well because the features the network learned in the convolutional layers are not similar to the features in an X-ray image. I have linked a couple of resources for obtaining pre-trained neural networks for transfer learning. These models allow you to take advantage of transfer learning and apply models designed for one use case to a different or more specific case with minimal overhead. It also allows for training on a CPU if that is all you have available. At the end of the day, transfer learning saves time and resources and allows for accurate results with little data, and it also allows smaller businesses and independent researchers to have the ability to develop powerful models.